Hello everyone. So in this video, I will solve some problems from the topic of relative extrema, the maximum and minimum values of a function. Okay. I'm sharing my screen from the desktop, and where possible, I will try to annotate on the screen itself and solve the problem, so I don't have to write the questions. But if I need more space, I might open a different document. Let us see. Okay. Um, First, I will discuss some very simple problems just to highlight the concepts and recap the main ideas. Here we have about finding the relative extrema for the functions with these graphs. Okay. The very simple questions here, but wanted to highlight that when you look at a point that is a minimum or a maximum, okay, for example, the point that I annotated here, it will be 1 comma 1 2 3 4 1 minus 4, right? So in that case, what we say is a relative minimum occurs at x equals 1, okay, and the value is f of 1, which is minus 4. Okay, so the relative minimum occurs at the x coordinate, and the value of the relative extreme is the y coordinate. That's all. Okay, let me scroll down if anything else is noteworthy. Sorry. Okay, in the absolute value function over there, at the point where there is a relative max, the derivative does not exist. Just wanted to point that out. Okay, the difference between the previous relative extremes where there is a parabola and the absolute value would be, those are the points where the derivative exists and the first derivative will be 0, whereas this is the other type of critical number, right? The other type of critical point where the derivative does not exist. Okay, similarly down here, and here you have one max, one min. I hope you can see my cursor in the recording as well. Okay, and similarly here you see a min, a max, and then another min where the derivative does not exist, again a corner, right? Okay, next I want to discuss about these problems of finding the points of relative minima maxima of different functions, right? The first few of them are all polynomials, and in the polynomials, the derivatives will always exist. So the only type of critical number you have to look for is where the derivative is 0. So you find the derivative, set it equal to 0, solve the equation, and while solving the equation, remember to factor out any constant number before you start solving the equation, so your equation will be easy. I'm thinking of that when I look at number 20 here. Okay, for example, here if I were to find the derivative, I'm going to write on top here to save space. The derivative would be 3x squared plus 6x minus 24, right? The constant 2 becomes 0 in the derivative. And now you can see it has the factor 3 everywhere. So you factor it out, you get x squared plus 2x minus 8. Now when you set it equal to 0, either 3 is 0 or the polynomial is 0, right? Now 3 is obviously not 0. That means the polynomial is equal to 0, and that's where you will get the two solutions. But that polynomial is better than the 1 before factoring. Okay. And similarly, um, problem number 23 here has been carefully designed so that you'll get rid of the factors, the fractions when you when you take the derivative. They have done the same thing in 24. Okay. Now, when it comes to problems like 25 and 26, they are power 4, right? The exponent, the degree is 4. So you might wonder, what will I do with the derivative? Okay. The derivative is going to have a cube and the x term. So you will have to find a way to solve those equations. So let me try first, okay, which equation becomes convenient and which not. I'll do 25 first. To find the relative extrema, in most of the calculation applications, finding the derivative should be the default step. Okay, take the function, find its derivative for x cube and then minus 36x. Oh, okay, sorry. Actually, these are easier. Fine. Because the constant becomes 0, so you have only this in your derivative. And I hope based on our previous discussion, you see what we should do, right? If you want to set it equal to 0 and solve, you have to factor it. Okay, always the technique is factoring, not like taking, keep the right hand side always 0, factor the left hand side. When factoring is not possible and if it is a quadratic equation, then we go for trying to use the quadratic formula. Okay, otherwise we go for factoring always. Now 4 is a common factor. Many students miss the number part, they just look at x and then x is a factor, right? So what you get here is x square minus 9. And I think I will stop at that. You know what to do after that. It will be x plus 3, x minus 3, in case you didn't know. Okay, or maybe let me write that step. A square minus b square. Okay, we have to remember the high school algebra. X square minus 3 square, and that factors as x plus 3, x minus 3 equals to 0. So you get 3 critical numbers, right? X can be 0 from the first factor, minus 3 from the second factor, and 3 from the third factor. So there are these 3 critical numbers. And you can, if you are using the first derivative test, I guess, in this exercise, and then you take the number line, or maybe let me discuss at least one problem in full. Okay. In the number line, you are going to mark those points. 0 is here, minus 3 is here, 3 is here, and then you are going to mark more points. Okay. In each interval, you are going to take a point. Minus 4 here, let's say, minus 1 here, 1 here, 4 here. Some simple numbers that you can evaluate the derivative for. Okay. And after you mark those points, you are going to evaluate the f prime a at those chosen values of a. Okay. Not the original function, the derivative. Okay. And while evaluating the derivative, we only need to know the plus sign and the minus sign. I think I spoke about this in my classes also. But if, in case you have forgotten, what I want to remind here is, we don't need to know the value. We only need to know the sign, whether the derivative is positive or negative at these chosen values, minus 4, minus 1, 1, and 4. Not the critical numbers. Okay, at the critical numbers, the derivative is 0 or does not exist. We already know that. We need to know in these intervals. And because we only need to know the sign, we don't even go back to the original expression of the derivative. Okay, what you do is you go back to the factored form. That's where your work will be very easy. Focus on that. Because, for example, when x is minus 4, let's look at the three things, x, x plus 3, and x minus 3, right? When x is minus 4, this is negative, that's minus 4. X plus 3 will also be negative because x is minus 4. So minus 4 plus 3, right? Negative, negative. And minus 4 minus 3 will be minus 7. That is also negative. So when x is minus 4, all of them are negative. That means the derivative is negative here, and I can indicate with this arrow it is decreasing. The function is decreasing. Okay. And when you plug in x equals minus 1, similarly, now I'm going to write plug in minus 1, and I'm going to use a different color for that. Let's say when I plug in minus 1, x is of course negative, that's minus 1, and x plus 3. Now minus 1 plus 3 will be positive, and x minus 3. Minus 1 minus 3 will be negative. Yeah? So positive, negative, negative, positive, negative. When you multiply, overall it becomes positive. So increasing. Similarly, when you plug in 1, 1 is positive, x plus 3 would be 4, that is positive. X minus 3, 1 minus 3 will be negative. So positive, positive, negative. When you multiply, the product is negative. And finally, when you plug in x equals 4, everything will be positive because even 4 minus 3 will be positive. So other terms are already positive, like that. Okay. And now that tells you that clearly this is a point of minimum, this is a point of maximum, and this is a point of minimum. Okay. And then you can find the values now, by the way. So the minimum and maximum, these values occur at minus 3, 0, and 3. The values of minimums and maximums are, you need to plug in these minus 3, 0, and 3 in the original function. Okay. So for example, here the value, okay, or let me just write that here. Values of the mean and max, for example, here would be f of minus 3. And you have to plug in minus 3 in the equation to get the minimum value. Okay. Minus 3 to the power 4 will be 81, minus the other one will be 9 times 18, which will be 81 times 2 minus 162 minus 4. So basically minus 81 minus 4 minus 85. 85. Okay. I'm not sure if this ribbon comes in the way of recording. Let me push this up somewhere. Okay. Minus 85. And so on. Okay. All right. I'll erase this now and discuss another problem. Then you see number 26 is similar. Yeah. 27. Okay. What is new about 27? Firstly, it is that is not a polynomial, and that means you have to be now careful. See, polynomials have derivatives everywhere, right? So I didn't have to worry earlier. But now that you see the exponent, especially it is 2/3, there are a couple of things we have to be careful when it comes to this kind of non-integer exponents, okay, which are fractions especially. So let me explain that by finding the derivative. At the outset, even if you before you find the derivative, you see its power is 2/3. Okay, so it is in terms of the radical, it is a cube root. That is important to understand. In terms of radical, that is a cube root. And the good news about cube root is defined for positive and negative numbers, right? But if that denominator, that 2 over 3, that denominator in that fraction, which is the exponent, if that is, and that has an even factor, like if it is 6 or 2 or 4 or anything which has an even factor, even number basically. If it is an even number, that involves a square root, right? Instead of 2 over 3, it was, suppose it was 3 over 2, other way, okay? Then it would be a square root. And if it is a square root, then your domain would only include the values of x that make it non-negative, you know. So that is the first thing I would ask you to be careful about when you are looking at things that are not polynomials. Okay. So actually I'm going to write that down here. It's important enough to write it. Okay. Uh, f of x equals 3 minus cube root of, let me write it in that form so you will understand it better. 8 plus 3x whole squared. Okay. Now that means we are taking the cube root and it's safe. Okay. Luckily, in this case, the quantity under the square root would be anyway positive. So, you can easily think of the cube root, but even if it is negative, does not matter. Cube roots exist, So what I'm trying to get at here is the domain of this function is all real numbers minus infinity to infinity. That is actually a thing I didn't mention for the polynomials, because for the polynomials it's understood by default the domain is minus infinity to infinity. That is not the case for other functions. So in general, for any function you have to actually think of the domain. Okay. um, because if the domain itself does not contain some points, then we don't have to worry about those points in the derivatives either. Okay. And that is one thing I wanted to say, but now this becomes interesting. See, the domain has all that values, so the function is defined for all real numbers, but the derivative will not be. And that is where we will get that second type of critical numbers. The values which are in the domain, but where the derivative does not exist. Okay. Let me see. I'm making all these claims. We'll find the derivative and we'll see. Let's find the derivative. And to find the derivative, I'm going to go back to the original form, not the radical form. Okay. I just wrote the radical form to illustrate that, it is a cube root there. According to original form, now the derivative of 3 is 0 minus the exponent is 2/3. Let it go to the coefficient, and I will get 8 plus 3x to the power minus 1/3, right? 2/3 minus 1. You subtract that, and then you have to multiply with the derivative of the inner thing, right? Chain rule. Okay, derivative of 8 plus 3x to the power 2/3. So x to the power 2/3 is 2/3 x to the power minus 1/3. But that x was 8 plus 3x, and the derivative of 8 plus 3x is 3. I need to multiply that according to chain rule. Okay, now the 3 and 3 cancel, minus 2 divided by, actually let me write like that, because that 8 plus 3x now it has a negative exponent, and it makes sense to take it to the denominator. Then it illustrates something, right? Now the derivative will not exist where the denominator is 0. Again, cube root, so no problem with positive and negative numbers, but the it cannot be 0, right? So critical numbers, for this particular thing, when I have to write critical numbers, there are going to be two types, and one of them doesn't exist. Okay, the usual one that we do, the derivative equal to 0, no value of x. You will not get any x which will make this derivative equal to 0. How? Why? Because the numerator is minus 2, a constant. Now you cannot divide minus 2 by anything and make it 0. Only when x goes to infinity, it will be 0, but that is not a real number. That will be an asymptote actually. Okay. So that critical number doesn't exist, but the other one where the derivative does not exist will give you the 8 plus 3x should be 0 in that case. Denominator has to be 0. So you get x equals minus 8 over 3. That is your critical number. Okay. And then again, because we are discussing first derivative test, let me quickly illustrate that. In this case, there is only one critical number, minus 8 over 3. So I'm very easily going to look at two numbers on the left and right. Minus 9 over 3 will be minus 3, that is on the left. And of course, 0 is on the right, the simple number that I can take. And if I want to now evaluate the derivative here. Oh, okay. I'm only scrolling the question. When I scroll it in my screen, I'm going to just write above that. Okay. Now, when I write the values of the derivative at those points, at minus 3, when you plug in minus 3 here, 8 minus 9. 3 times minus 3 is minus 9. 8 minus 9 is minus 1. Cube root of minus 1 is minus 1. So basically minus 2 divided by minus 1, which is 2, which means the function is increasing there. Okay. And when you plug in x equal to 0 on the right side, by the way, these are the values where I'm evaluating. This is the critical number at the middle here. Okay. That is where the derivative is 0. And when you plug in 0, of course, you get 8 to the power 1/3, which is cube root of 8, which is 2. Now, cube root of 8 is 2, not minus 2. Okay. Cube roots are simple, like positive, positive, negative, negative. So cube root of 8 is 2. Minus 2 divided by 2 is minus 1. So, of course, that means the function is decreasing. Okay. Hence, the conclusion will be that the value x equals minus 8 over 3 is a point of maximum in the graph where the derivative does not exist. That is interesting. Okay. The original function exists there. And the value of the function would, of course, be, I think, wouldn't it be just 3? Because because the critical number was obtained by making that 8 plus 3x equal to 0, So if you go back to the original function, it's easy to see the value is 3. Okay. So I'll write here max value equals 3 at x equals 8 over 3. Or sometimes, by the way, we also talk about point. Okay, so you can say, or you can just write the same, you can mean the same thing by writing 8 over 3 comma 3 is a relative maximum. Point of relative maximum or relative maximum. Okay, it is understood when you write like that. A more detailed proper way of saying would be that 8 over 3 comma 3 is a point of relative maximum. Okay. And because the derivative does not exist there, I'm just curious. You might want to graph this and see how that happens. And my guess is because the function is still continuous. There is nothing that makes it discontinuous at that point. Because it has only cube root and there is no denominator, so there is nothing to make it discontinuous. Okay. That means it has to be a corner, right? You have to sketch it and or plot it on a Desmos and see. Okay, so let me again recap here. I did the whole problem, but where I wanted to start with and mainly focus on while discussing this was for non-polynomials, you might come up with a situation where the derivative does not exist. And now, important thing is that point where the derivative does not exist should be in the domain. Okay, So here the domain was minus infinity to infinity. Domain of f was that, but domain of f prime did not have minus 8 over 3. F prime did not exist at minus 8 over 3. That is why it is a critical number. If that minus 8 over 3 was not in the domain of f itself, then I would not worry. In fact, I'm going to discuss another problem like down related to that. But even in this case, I can actually modify the problem and show you. Okay. In which case it will not be a critical number. If the function was 8x, sorry, 3 minus 1 over 8 plus 3x, let's say, to the power 2/3. Okay, I'm just like showing you what is the difference here. Instead of being in the numerator, if that 8 plus 3x to the power 2/3 was in the denominator, then the function f itself does not exist at that minus 8 over 3. Okay, so the domain of f in this case, the domain would be minus infinity to minus 8 over 3 or plus 8 over 3. Sorry, minus 8 over 3. What am I? Okay, I've been writing 8 over 3 for a while in the past discussion. That's minus 8 over 3 everywhere. Sorry about that. Okay. So minus infinity to minus 8 over 3 union minus 8 over 3 to infinity. That is how I will write the domain, just avoiding the point minus 8 over 3. Right? So because it's not in the domain, your conclusion later on, like when you find the derivative, your answer would be no critical numbers. That function has no critical numbers because we have already seen the first type of critical numbers will not exist because the numerator will be a constant. When you find the derivative of that, you'll still have it in the denominator. And the second type of critical number where the derivative does not exist, okay, for that the derivative does not exist, but the function also is not defined. There is only that one point x equals minus 8 over 3, but even the function is not defined there, so it's not even in the domain, so that critical number will not be considered. Okay, so you will basically say no critical numbers. That means no relative extrema. This new function that I defined will not have any relative mean or max. Once again, I would recommend graph this in Desmos, or actually why not I do it. Let me see if I can do that, and I'm going to type that. Okay, quickly, and I need to, I think, change my screen to show it to you. Okay, so let me type the two functions. Okay, the first function was y equals 3 minus, in parenthesis, 8 plus 3x whole to the power 2 divided by 3. Yes, very nice to see. See that point. Okay, that point is where you have max. Then if I were to type y, and you can clearly see that is a critical number because the derivative does not exist and it's a relative maximum, right? Whereas if I did y equals 3 minus 1 divided by 8 plus 3x, let me see whatever I was saying in theory, if that is true or not. 2 divided by 3. Okay, now that would be the case. See, the blue one is the new function. At the same x value, the derivative does not exist. But that problem is that line actually is an asymptote. You have to zoom and see. Okay, if you zoom and see, it's an asymptote. The function is not defined at that point. It goes to infinity, minus infinity on both the sides. In that case, the derivative does not exist, but it's not in the domain. The point is not even in the domain. Okay, so it is not a critical number. See, that is the difference. Here it is a critical number because the point is in the domain. Okay. Or I don't know if in some textbooks they define critical number in a different way. But even then you can say in relative max and min, we are concerned about critical numbers that are in the domain. Okay. All right. I think that is enough discussion on that. Let me go back to the book. By the way, these videos that I'm recording, these are all I'm recording on Zoom, okay, and they will not give you what you call. It doesn't give you more than 40 minutes, okay, unfortunately, and I will let you know when I'm running out of time, and then I will record another video, okay, for more things that I want to discuss. Okay. I think in a way it's good for you as well. You can watch only one video at a time and pay full attention. Moving on, number 28 is fine. You'll find similar situation with number 29, for example. Okay, read the question there. In 29, you'll find that there is x to the 2/3. So the derivative will have x to the 1/3 in the denominator. So the derivative does not exist at x equal to 0. Okay. And not all exponents are of the same type. That is illustrated in number 30. You have x to the 5/3 in the first term, and its derivative will be x to the 2/3, still positive, So no issues. So the derivative will exist. X to the 2/3 will exist everywhere, right? But whereas the second term will have the same situation like before. So basically, if that exponent is less than 1, then you have a problem, right? When you subtract 1 in the derivative, it goes to the denominator. That is the moral of the story. Okay. And number 33, again, to highlight the same thing, or maybe I think I can highlight like this once in a while to show you. Yeah. Sorry, why that? I can actually circle it here. Okay. In number 33 here, again, the situation is like what I was just showing. It's not even in the domain. That x equal to 0 is not in the domain, so it's not a critical number. So there will not be any max or min for this function. No, there might be. I'm sorry. When you take the derivative, x will give, the derivative of x will be 1. So 1 plus 1 over x square. It may be, yeah, when you solve the equation and if you get some values of x, by derivating being equal to 0, you may get those critical numbers. I don't think you get that here, but you may. What you will not get is the not existing, the derivative does not exist type. That will not be the case here. Okay. 0 is not in the domain. Okay. Yeah, the difference between 33 and 34, I'll tell you. In 33, when you find the derivative, let me just only write that part. Here you will get x plus 1 over x square, sorry, 1 plus 1 over x square, the derivative. Okay, so when you try to solve that equal to 0, you will not get any value of x because you are saying 1 plus something positive is equal to 0. That's not going to happen, right? You'll get only imaginary numbers. So no critical numbers for number 33. Okay, x equal to 0, as I said, is not a critical number because not in the domain. But if you look at number 34, the derivative will be 2x minus 1 over x square. Now you try to solve the equation, you will get the values of x. And I think it's particularly cube root of, you can solve it, okay? I'll tell you. X cube 1 over 2. So basically 1 over cube root of 2. That is what you will get. Okay, and that's a real number, So that is the difference between those two things. And that will be a critical number where the derivative is 0. Okay, if you set this equal to 0, then you get that. Okay. Similarly, just to For number 35, I think I will talk about that in the next video, but I will tell you the highlight in this video. Okay. X equal to 3 is not in the domain. So for number 35, the domain will be minus infinity to 3 union 3 to infinity. Okay. Now, then you will find the derivative and set it equal to 0. And where the derivative does not exist would be still the same point, x equal to 3. We don't consider that. But you can set the derivative equal to 0 and find some values of x, right? What I will be showing in the video is how to find the derivative of this type of particular functions, um, which are both polynomials. We call them rational functions. Okay. Now, we studied this in college algebra, so some of you might be a little hazy about this. You can use quotient rule, but I would say that is the hard way, okay, difficult way. I'll show in my next video a simple technique to find derivative, which will make your life much easier. Okay. And then in the next video, I'll find the derivative of this and then I'll go down and discuss more things. Okay. All right. See you in the next video.